Okie dokie. So in this video, we're going to prove that theorem we mentioned in the last video about perpendicular lines. So, or at least we're in half of it in this video. So if two lines are perpendicular, if and only if their slopes are negative reciprocals. Again, note this if and only if part. So this means it's one statement plus its converse written into one. So the two statements are, if two lines are perpendicular, then their slopes are negative reciprocals. And the converse of that statement, is if two slopes are negative reciprocals, then their lines are perpendicular. So in this first video, we're going to take a look at this first one here. So let's draw a picture here. I have two lines, or sorry, there's my axes. I'll draw my two lines. Draw this red one. Will look like that. And since they're perpendicular, they must intersect, of course. And let's draw this one right here like that. Okay, so we know that it's perpendicular. And the question is, so let's say that this is the red one is line 1. And let's say the purple one is line 2. So the theorem wants us, or the proof for this, we would have to show that, or prove, M1 is equal to, the reciprocal of M2 would be just 1 over M2, and also negative. Okay? So one of the things that comes up a lot when you're talking about proofs that come up algebraically, so since this is an equation, there's going to be a lot of algebra involved, is to think about it in other ways. And so maybe in my mind, in my plan for my proof, I don't know how I'm going to get M1 to equal 1 over M2. But if I do a little bit of rearranging, I could multiply both sides by M2 and see that M1 times M2 is equal to negative 1. And so if I could show somehow that either of these is true, then I'm good, because these are the same equation. They're equivalent. Okay, so let's get into this. And again, I urge you to pause it here and just try something. I would start off with this. Let me just give you a second to get started before you pause. Let's pretend to just intersect at some random point here. Call it P comma Q. That's their point of intersection. So take a minute, pause the video, try something out yourself, and just see what happens. All right, I'm going to assume that you tried it. So what I'm going to do first is I'm going to draw in an altitude from this point P comma Q. So I'm going to draw that down there. If we remember from our exploration of the right triangles months ago at this point, once you draw this altitude down, you get a lot for your money. So this altitude, since it came from PQ and just dropped straight down to the x-axis, that altitude, that h, is actually equal to q. So I'm just going to write in q there for that length. Okay. And I'm also going to split up this hypotenuse of the right triangle, because again, because we know it's perpendicular, this is a right triangle. So I'm going to call this part right here, I'm just going to call that B, and I'm going to call this part right here A. There's a reason I did this, of course. So if I look at this yellow triangle right here, it's a slope triangle, right? So whenever you have a line and you draw a right triangle where the line itself is the hypotenuse of that right triangle, you're drawing a slope triangle, if you remember from Algebra 1. You might have done this in Algebra 1. Now I can actually get my slope from this. So for the second slope, M2 right here, well, it's rise over run, of course. So my rise in this case is Q, but I'm going downward. So I'm going to say it's negative Q. And my run, well, I went over to the right, A units. So my slope, or my run is A, and so my slope number 2 is equal to negative Q over A. Similarly, I'll draw a slope triangle here with this blue one. And this will say that M1 is equal to, again, rise over run. So my rise, I went up Q this time, so I'm just going to leave it as positive Q. And I ran B. Now we can take a look at this. Well, let's see. if I multiply now m1 and m2, because what I'm trying to do is, hey, I have an equation for m2 and m1, or values for m2 and m1. If I multiply them together, will it just come out to -1? Let's just see what happens. So let's see, m1 times m2. Well, let's substitute these in. And I'll get, let's see, q over b times -q over a. And the question is that equal to -1? Well, let's see. If I clean this up, I'll get -q squared over ab. Well, that doesn't really look like -1, unless we could somehow show that q squared equals ab. Because if that was the case, then we could just substitute in and then we'd be good to go. Wait a minute. If I remember correctly, there's something magical that happens when I have a right triangle, this giant right triangle, in this case, this big orange one, and then I draw that height. If we remember what that is, well, there are several things that came out of this, but the one that's going to be helpful here, the height, which in this case is q, is the geometric mean of a and b. Remember, those are the hypotenuse segments. The hypotenuse segments. All that translates to algebraically is that q is equal to the square root of ab, or you could say that q squared equals ab, which is exactly what we were trying to get at. So now if I just substitute in -q squared over ab, replace the q squared with ab, equals -ab over ab, which is -1. Remember, what did this first q squared over ab mess come from? That came from m1 times m2. And therefore, let's just bring those together. We can say finally, m1 times m2 is equal to -1, which is, again, the same thing, logically equivalent to, that's the triple equal sign there, m1 equals -1 over m2. So hopefully that proof made sense. And now we know why, if two lines are perpendicular, then their slopes are negative reciprocals. Another way to say that is if two lines are perpendicular, then the product of their slopes is -1. And that's kind of the way we proved it. But again, those two equations are equivalent, so the proof did not matter if you end up with one or the other.